We are very grateful to have Alexandre Adler here speaking with us tonight. And so Alexandre Adler is a postdoc in the physics department working in Professor Adrian Lee's group. Most of his work focuses on simulating possible sources of measurement error in CMB telescopes due to limitations of the instruments. In particular, he works on the Simons Observatory, a series of telescopes in the Chilean Atacama Desert, and on Taurus, a telescope that will be carried to the stratosphere by a NASA balloon. Before coming to Berkeley, he studied in Switzerland, the UK, and France, and completed his PhD in Stockholm University in Sweden. We're so grateful to have him here today with us, so please take it away.
Hi, everyone. In summer 1964, Arno Penzias and Bob Wilson were cleaning pigeon poop from inside an antenna. So this is the antenna. It's in Holmdel, New Jersey. As you can see from the size of the people, it's quite large. And at first was built to detect radio waves bounced from big spherical satellites filled with air that were some of the first satellites, some of the first communication satellite experiments. After that was done, the Bell Laboratories had just a nice telescope and nothing to do with it, and so they gave it to two of their astrophysicists called Arno Penzias and Bob Wilson, and they wanted to use that antenna, which they thought was very nice, to measure the flux, so to measure how much radio waves came from different places in the sky at a wavelength of 2 inches and 7/8, or in units I understand, 7.5 centimeters. And they liked and they thought, oh, it's not the biggest radio telescope in the world, but it's a really sensitive system, and because it has this really very specific shape, it's only sensitive to whatever ends up entering here. So if we point it somewhere, we can really have a good directionality. And so they thought they would understand everything they would measure. Now, they thought they could measure the absolute amount of light coming from anywhere they pointed at. And what they would do is they had a big vat of liquid helium, which has a very set defined temperature of almost absolute 0, 4 Kelvin. And they had an electronic machine they tuned that added a few kelvins. And so they knew they had a reference source at 7.3 Kelvin. They had an electrical switch they could operate to either look at the reference source with the apparatus or look at the sky. And they said, okay, we can measure that the atmosphere emits light that is like a few Kelvin. Yeah, I don't know. Has there, like, if you have ever bought a light bulb, you know there's like a temperature written and it gives you like the warmth. So it's the same idea. There is a temperature that's associated with a luminosity and a color. It's called like a black bulb. For a given temperature, there's a given luminosity and color that matches. And they know the atmosphere is kind of like a black body at 2 Kelvin. The waveguide, which is the little tube that took the light from the atmosphere, from the sky or from the antenna to the detector at the end, is 2 Kelvin. And long story short, they say, okay, the whole thing we're measuring is 4 Kelvin. And so they were left with 3 Kelvin they couldn't explain. To balance out the temperature of the antenna that the antenna measured and the temperature that the helium was kept out, they had to have a 3 Kelvin signal they didn't know about. And so they were very puzzled. They thought, okay, maybe we don't know the antenna very well. There were a few pigeons who laid there because it was quite warm compared to the New Jersey winter that winter. So let's clean out the pigeon nest, clean out the pigeon poop. Let's put masking tape on any rivets we have on the antenna, because maybe those are messing up our measure and we should have the smoothest surface on the antenna. And then one of them went to a talk at MIT where the professor was discussing, oh, there are people in Princeton, so the people on the right, I guess, several years later, who are making an experiment to measure the cosmic microwave background. They think there's this background radiation at a few Kelvin in the universe. And so, very excitedly, Wilson called the professor in charge on the right, which is a man also called, well, Robert as well. So Bob called Bob and said, hey, we found something. I think it's the thing you're looking for. And apparently, Pence just put down the phone, looked at this research group which was building a similar apparatus and said, boys, we have been scooped. So that's what scientists say when someone else publishes your result before you. So someone had found the signal they were looking for. And so this is the start of modern cosmology, which is the field of studying the universe's beginning and evolution. And since then, the cosmic microwave background has been studied again and again in greater and greater detail. But in 1964, when they discovered it, all they had was, there is some signal in the sky that's the same in all directions, and the temperature is 2.7 Kelvin. And what Dickey's group had figured out was an argument that goes something like this. So in the beginning, there was the Big Bang. Everything was hot and dense, and there were no atoms, there were just light and elementary particles bouncing around. And the universe had an impulse to grow. That initial explosion gave it, made it growing, and so the distance between things started increasing. The density of the light, the density of the elementary particles decreased, and because of that black body relation, when you had less stuff around, the intensity of the light also decreased, because as the universe expands, the light stretches out, and as it stretches out, it loses energy. And at some point, there's little energy, like the energy of the light is not enough to disturb the formation of atoms anymore, and so the first atoms will form, and that means the light has nothing to bounce off of anymore and just goes straight. And since afterwards, so that's the CMB, and afterwards, the first stars formed, the first galaxies formed from the first stars, even larger things forms from galaxies clustering together, and then we have the sky of today. And as I was saying, we have been measuring the cosmic microwave background with even more precision since the 60s. And at first, Pence and Wilson were saying, oh, we have found this thing that's the same in all directions, except there's a bit more microwave coming from the galaxy itself. Our galaxy also makes microwave light. Okay, but in the 90s, a team in Berkeley, led by a professor in the astronomy department called George Smoot, launched a satellites and discovered that no, there are variations. But they're actually we're very happy to see there were small differences in the temperature, like depending on where you look. They're very small. It's like 1 in 10,000. You couldn't see, if it were like visible light, you couldn't see the difference in hue by eye. It's like very small differences. But it's fine, because in the 60s, after the discovery of the cosmic microwave background, other people thought, oh, what are the implications? How do we go from that thing that's the same in all directions to stars and galaxies? There needs to be small differences that aggregate into becoming big differences. But we've mapped the CMB again with experiments from the ground, from space. So that was a satellite called COBE. Then in the 2000s, there was one called WMAP. You see, like, get a better resolution, both like sensitive to smaller differences and also being able to look at smaller details. And then in the 2010s, and I'm sorry it looks a bit pixelated on this screen, but it gets quite high resolution. There was a satellite called Planck. You can also observe it from the ground. So on those maps, which are kind of like, think of it as a, you know, an atlas when you see the whole world projected. So this is the whole sky, the whole sphere of the sky projected in this shape. And little differences in color correspond to little differences in the temperature of the sky measured in that direction. So I talked about it before I was supposed to, but bear with me. So this is what is the sky like before the CMB. You have protons, which, as everyone knows from textbook illustrations, are red and big. Electrons, which are blue and small. And then you have nuclei of helium, which it's not that important, but it is there, so I wanted to put it. But it basically, everything is in a state called the plasma. Plasma is when matter is not made of ordinary atoms, but it's made of a mixture of charged particles. And here the charged particles we have are the protons and the electrons. And they're all bathed in a truly gigantic amount of light. So the particles or waves, whatever, that carry light are called photons. And the photons can only interact with charged particles. They don't really interact with, they won't interact with the neutrons that are, for instance, in the helium nuclei, but they will bounce off the protons, bounce off the electrons. And so everyone is kept roughly at the same energy, because if, let's say, a photon has a bit too much energy, it will bounce off an electron, cool down a bit, the electron will get a bit of energy, transfer it to another photon next time it bounces into it. So everything's in this equilibrium. And the last secret ingredient is dark matter. But dark matter, we don't really know what it is, we just know it exists. And the only thing we know about it for certain is that it obeys gravity the same way as normal matter, and that's actually the only thing it's sensitive to. And there's much more dark matter than normal matter. Now, because the dark matter doesn't get to bounce around with the electrons and the photons, it just wants to obey gravity and so collapse on itself. So the dark matter will drag and create more and more important gravity wells. Well, the normal matter also feels gravity, so it will follow the dark matter and get compressed tighter and tighter and tighter until it's too tight. The photons, they want to keep going straight. They apply pressure to the matter, and so the matter bounces back out. And this cycle, the dark matter keeps collapsing as the normal matter bounces out, and this cycle continues several times. It's like a spring coiling in and out. At some points, the temperature drops, as I say, the atoms form normally, and the photons have no one left to play with, but they just go straight, across the whole universe from that moment in time, only 400,000 years after the Big Bang, to today, 13.8 billion years later. And that's what Penzias and Wilson saw. That's what we saw with COBE and WMAP and Planck and other telescopes. That's what all the ones among you have seen on your CRT monitor when it was on your TV, when it was between channels. 1% of the static you saw on the screen is CMB photons. That references make sense to fewer and fewer people every year. So, yes. Now you might ask, but those cycle of oscillation, what happens to them afterwards? So, what happens to them afterwards, when the CMB forms, the oscillation have frozen into a pattern of expansion and contraction. And this means that there's areas that will have been stuck in a cycle of compression that will be more dense, and those that will be stuck in a cycle during the expansion phase and will be less dense. And those are the seeds, those extra density is the seed from where the galaxies we live in and all the galaxies in the universe come from. Those little tiny chance variations of where you were in the cycle, if you were in an over and under density, is where our galaxies come from. And in fact, today, we can measure who was in the most, yes. Today, we can say, okay, what if you had just the time to collapse, no bouncing between the Big Bang and the moment the CMB happened? No bounce, just one collapse. That is going to be the strongest motion you can have. It's going to be the strongest motion you can have because the cycle of compression, expansion gets dampened by the dark matter just wanting to compress, not do the expansion part. So it's like a slinky that is gradually like losing energy as it goes up and down until it stops. And the first motion, just one compression, that is going to be the most common blotch size in the universe. So there will be a size associated, there's a time associated with that free fall towards compression. If you know the speed at which particles move, you can calculate how much distance they have covered to make that time, for that time. And you can say, okay, so the most likely distance between two little over densities is twice that distance, right? Because one of them will have fallen in one direction, the other half will have fallen in the other direction. And so you have a distance at the time of the cosmic microwave background. The universe will keep growing and growing. Those little seeds of overdensity will keep gathering matter, creating the first stars in the galaxies, first galaxies. And so today, when you look at the distance between two galaxies, then there is a most likely distance between the two galaxies that corresponds to that. So by measuring here, we have this curve of like probability to find a galaxy. By measuring the distance between billions of galaxies, we have found that there is a slight over distance, and that corresponds exactly to what is predicted by looking at the things of by looking at the tiny little splotches in the cosmic microwave background. Now, sorry, this is the most math, I swear. Maybe the second most math. But what we do as cosmic microwave background scientists is we make those maps with our telescopes, and then we look at the separation between points in the map, the angular separation, and we say how correlated, so how likely it is that if you find a temperature here, like how likely is it you're going to find the same temperature there? And so we built what we call an angular power spectrum, which if you've ever played with a stereo or thought about like sound waves, whatever, you know, like you can take the sound and Fourier transform it to a spectrum where like, oh, there's a peak, there's a resonance here. If you have a tuning fork, if you ever like struck a tuning fork, there is like one frequency at which it rings. So this is sort of the same, but like in space instead of in time. So there are frequencies, there are distances, separations on the sky, which have a lot of correlation between each other, and there are those that don't really. And that's what those kind of graphical power spectra measure. So you can see the characteristic scale of what we call anisotropies, which are the tiny differences in temperature in the cosmic microwave background, is about 1 degree. So if you hold your hand out, it's the size of a finger. So as you go out in the sky, as you go out on the terrace, hopefully later, you can hold out your finger, look at the night sky, and even though you can't see them because they're microwaves, so we can't see them with the naked eye. Otherwise, it would be very blinding to reheat your lunch. Once you look in the sky, you know there are those patterns about the size, about the width of the finger. Okay. With your arm stretched out. Otherwise, it doesn't work. Yes. I'm going to need audience participation for this one. I need a volunteer. Who wants to volunteer? It's right. I have a bunch of sliders, and the goal is to change the sliders so that the CMB you get from your simulated universe matches the one of our universe. Who wants to try? Yeah. Sorry, behind you had a hand. Yeah, in the yellow, in the black and yellow. What's your name?
Kai.
Okay, let's Kai. That's right. Right. So yeah.
So wait, is this diagonal line like the separation?
Yes. So you can see as you change this. So.
I see.
So we have three sliders. One for the normal matter, so the protons, the electrons. You need a bit of normal matter because we exist. The dark matter that only follows gravity. And then dark energy, which gives a kick to the universe towards for the last 5 to 10 billion years. It doesn't really matter to make the CMB, but it does matter because if it gives a kick to make the universe expand faster, the CMB will look small. So yeah, you see this, try to get the similarity score as high as you
I just now
can.
noticed the percentage.
Yes.
Oh, I see, that's higher. I see this is way off. Oh,
Okay, we're getting there, we're getting there.
I see, I just said this way too.
Oh, almost there, almost there.
Oh, wait.
Yeah, I think.
Wow.
So
What?
it
What did that do?
flatten makes it so that the sum of the three values is 1.
Ah, I see. That's
And
dubiously useful.
oh no, it's actually pretty good because our universe is actually flat. Yep. So
What if the normal matter only does?
well, it doesn't look like our universe.
Oh,
So
it gets rid of everything.
it's except the normal matter. So the CMB is the strongest proof we have that dark matter exists because we cannot make it with only normal matter. Thanks, Kai. Right. So. There we go. So, as Kai was changing the amount of stuff in the universe, they were also. Which one was it? They were also changing that power spectrum. So there's a one-to-one correspondence between like. See, if I add normal matter, then the size of the peak grows because there's more stuff collapsing. The size of the second peak, which corresponds to contraction and expansion, starts shrinking. If I add more dark matter, then the collapse starts dominating, and so you don't really get more peaks. The dark matter kind of damps the oscillations too much. But yes, so that is how we know from the cosmic microwave background. And I should go back to full screen. Is that full screen? That is how, with the cosmic microwave background, we're able to measure the 6 parameters that make up the universe. We are very lucky that we only need 6 to describe everything that has happened on a scale larger than a galaxy. Like, other people will say, no, there are other things, there's stars, there's baryonic feedback and supernovas and quasars, but no. It's an astonishingly simple object to study. Everything that happens in those first 400,000 years is reducible to a few equations. Maybe there's a bit of sweating around to solve that equation, but we have computers that do it in a couple of seconds. And we can create, like I did earlier, like little versions of universes based on all those 6 parameters. And by creating many versions and then comparing them to the universe we have, we were able to figure out what are the values of those 6 parameters. So the normal matter density, the dark matter density, the geometry that tells us like how fast the universe has expanded since then, the optical depth to reionization. I'm going to come back to this one. This is a nice one that actually involves a bit of astrophysics. Okay, maybe there is a bit of astrophysics, but you don't need details, you just need the big. And those 2 parameters talk about the NS and AS, talk about what the initial conditions of the universe are. So at the Big Bang, what creates the first little over and under density in which those oscillations of matter and radiation do take place, and it then grow to be the seeds of stars and galaxies. So I showed maps of the CMB, but I didn't show like how we measure it. Like I talked about cleaning out pigeon poop. We don't do that anymore. We've moved to different places. Now we have cute little animals called vizcachas that look a bit like a mixture between a rabbit and a hamster. They're adorable. I don't have a picture there. I think we should have. But it's still the same idea that we need to be very cool because we are trying to measure something that is a few kelvins. We need our telescope to be colder than that to be able to measure small differences of. So we measure differences that are on the order of microkelvins. So that's 1,000,000 times smaller than a Kelvin. And we have really impressive fridges that can cool down the cameras we have in our telescopes to 0.1 Kelvin, so almost minus 460 Fahrenheit. So this is one of the telescopes I work on. It's called the Simon Observatory Small Aperture Telescope. And you have those big things are to stop light from the sun or surrounding mountains to enter the telescope. But then the telescope itself is a fairly, is like 6 foot by 5 foot box with, we have a window at the front so that you can see inside what you want from the fridge, or so that light can get in. Then we have a few lenses, and at the bottom we have what we call detectors, which are sort of like a digital camera. And then the rest of the space is occupied by keeping a vacuum and keeping the thing cool. So because we're looking for very small changes in temperature of what the detectors measure, we need to really keep it isolated from any sort of outside interference. And a big part of my work is simulating those outside interferences and seeing how they change what the telescope measure and thinking of clever ways to filter out this noise from the telescope signal. So we don't really take pictures of the sky. What we do is instead that we have all those detectors in little rows. So this is the kind of detector. This is what we call an array of pixels. So they're, each of those is sensitive to the temperature of the light that comes in through a very complicated system that frankly it's not important to know the details, but we have And what we do is we move around telescopes. In the case of Planck, it just spans what's spinning into space. But as it moves, we know where it's pointing. And by looking at like several hundred times a second at the very nearby points, we can say, okay, so when I was pointing there, I measured this temperature, and then I was pointing there, I measured this temperature, and by doing that again and again and again, we build maps of the sky. And yeah, this is how we get the Planck map with the galaxy in the middle. Right, so you noticed I talked about, I was introduced as saying I work in Chile. I worked on the telescope in Chile, so that's the one on the left, the Simons Observatory in the Atacama Desert. I think it's 5,000 meters, that's 16,000 feet, 15,000 feet up. So that's pretty high up. It's one of the driest places on Earth. In the middle, there's a picture of the South Pole Telescope, which is, well, the name says it, at the South Pole. We have also people in Berkeley working on this. They're really nice. And satellites like that, we send in deep space. So why do we need to go to why can't we build a CMB telescope in the backyard? I mean, the first people, they built it in suburban New Jersey. Surely we should have margin. So does anyone want to make guesses why we need to go to remote places? Yes?
Less air pollution and specifically in space, less interference from the Earth's atmosphere. I don't know.
Less interference from?
The Earth's atmosphere.
Yes, that is the right answer. So, exactly. The atmosphere is transparent to normal light, which is nice because otherwise our power bills would go way up. Also, all the plants would die, so it's nice that it's transparent to normal light. It's transparent to radio waves, which is good for people who do radio astronomy. And it's opaque to much of the rest, which is also very good because this means you don't get sunburnt on a cloudy day, or you don't get an X-ray every time you step out of your house. But it's not great for people who want to observe microwave or infrared like us. So if you look at the plot on the left, this shows how transparent the atmosphere is at different frequencies. So light has every photon has a given energy. It's the same as saying every photon has a given frequency. So this is in gigahertz. So how many times the photon's electric field changes per second. And that also means it has a wavelength. So CMB photons, the wavelength is roughly between an inch and 1/10 of an inch, or centimeter to millimeter. And so this is roughly I'm really not good at customary units. So basically we can observe the CMB at the low frequencies, so more towards the inch. So less than 200 gigahertz, the atmosphere is fairly transparent. The different curves indicate different amounts of water vapor, because water is a very good thing to absorb microwaves, which is why the microwave you have in your kitchen is efficient. It's because it can, the microwaves can excite the water molecules in your food and heat them up. And you see the more water vapor there is in the atmosphere, the less transmission you have. And beyond 300 gigahertz, so 1 millimeter or 1/20th of an inch, I think, the atmosphere is not transparent and you have to go to space. So this is why things like Planck are really important, because we can get a handle on the cosmic microwave background at high frequencies that way. And anyway, this is what a time stream, so this time data that one of the detectors measures as we scan looks like. So you can see it keeps jumping up and down, and only by averaging over those hundreds of times we observe per second are we able to get an actual signal. So this is before processing, and then we do a bit of signal processing, and we get a more reasonable fluctuation. We get clean a signal. And that's, so the two tricks we have to measure the CMB with our detectors, measure those small things, is to have lots of detectors and keep them as isolated and full as possible. So now we have tens of thousands of detectors looking hundreds of times a second at the same patch of the sky, and then moving on as the telescopes move to just the next little patch blob, just the next little blob, just the next little blob. And yeah, that's how we do progress. That's how we measure the CMB better and better. Okay, so I talked a bit about the galaxy. There's lots of stuff in the galaxy, and it's kind of annoying because I'm interested in the cosmic microwave background, and I cannot see through the galaxy by myself. It's like if you were sitting in front of the TV and someone was standing in front of you, you can't really see what they're saying. Maybe. See? So, but the nice thing is they're all different from the cosmic microwave background's black body temperature. They all have a different way of scaling their temperature and their emission with the frequency of the light you measure. So on the top left, you have something called synchrotron radiation that is due to electrons spinning in our galaxy's magnetic field near the center of the galaxy. Then, for instance, at the bottom right, you have just the emission from dust grains in our galaxy. Our galaxy is mostly hydrogen gas and dust. Stars are only a few percent of the mass, but the dust is quite cold, which is why we can see it in the microwave and not in the visible light that well. In the visible light, we see, if you've seen the Milky Way, you might have seen black bands through it. That's the dust in visible light. It absorbs the light that would come from the center of the Milky Way, but in infrared and in microwave, it emits light. So what we do is we measure the sky at many different frequencies, and you can see like how every map here is at a different frequency, and each of them has like a different pattern made by the galaxy. So by combining them all together, we can derive what the emission laws for all those different astrophysical components are, and subtract them and recover the clean CMB map that I showed in the beginning. So instead of having to throw away 80 or 90% of the sky, we can get better maps. But that is also why it's important to go to space and not just observe at the frequency we can observe from the ground. This dust emission can only really nail it down fully by going to space. Right, so that's where we are so far, right? I've talked about the CMB monopole that was detected in the 60s, the anisotropies that are due to those tiny variations in matter and radiation density at the beginning of the universe. I've talked about the foregrounds, the atmosphere, the instrument, the noise of the instrument, so the idea that even if it's kept almost at 0.1 Kelvin, there will still be like heat generated by the instrument that will hit our detectors and make our measure a bit worse. And now I'm going to talk a bit about the rest. So you see those two things are E modes and B modes, and there's this thing called gravitational lensing. So let's start with E modes and B modes. So who here has a pair of sunglasses somewhere? Not with them, but at home. Or even with them, actually. Something we can show. Oh, I have mine too. 1 second. Right. So if you see light as a wave, exactly, it's going in one direction, and the thing that's oscillating is the electric and the magnetic field in the other two directions. And so if you can, I hope it works. I think my I think you need maybe 2 pairs. Yeah, you need 2 pairs because the first one literally polarizes. Can I get the second pair of sunglasses? All right. From the gentleman in front.
They say they're polarized.
Oh, let's find if there's a few more lights. Okay. Actually, can I get your help?
Sure.
Set up the second pair.
All right.
Right, so the idea is the first pair of sunglasses is going to linearly polarize the light, so it's going to select one plane in which all the photons that go through will be like oscillating in one plane. And normally, so if they're aligned, can you see the light through? Okay. Now can you see the light go through? Still? I guess mine are polarized. Okay, well, experiments don't always work. That's a big lesson in physics. But basically, you can select, so you can think of linear polarization as choosing one specific orientation for the light to oscillate as it propagates. So, most light is not polarized. On average, you'll get photons with all polarization arriving somewhere. So on average, there will be no net polarization. But it turns out that electrons are slightly sensitive to what the polarization of light hitting them is. And so the angle at which you're scattered will depend on, at which the photons will be scattered, will depend on the light's polarization as it scatters. So what happens is, if you have, this is the most complicated part of the talk, I swear. If you have differences in the energy of the photons that are around you as an electron, you will preferably send out a specific polarization in a specific direction. And the pattern that causes this, the pattern you are sensitive to, is called a quadrupolar distribution. So it means there are 2 areas that are warmer, have more energy around you, and 2 areas that are colder or have less energy around you. And if you remember that plot I showed of transforming the sky map into just an angular correlation function, there will always be a quadrupole term around you. So the sky you see is the sum of monopole terms, so the basic CMB, plus a dipole term with 1 plus and 1 minus, plus several quadrupole terms with 2 pluses and 2 minus, plus. You can keep going until like infinity. There will always be a sum of what we call spherical harmonics, which is how you can decompose any signal on a sphere, any function on a sphere, into the sum of those mathematically regular patterns with a specific scale. So the quadrupole, the specific scale of the quadrupole is 90 degrees. So between a very hot spot and a very cold spot, it's 90 degrees. Between the plus and the minus, 90 degrees. And so the mode that the main CMB excitation is at the multipole, so the old poles are 200, so that's the 1 degree excitations I was talking about earlier. But suffice to say, the electrons in the primordial universe, there will be slightly warmer areas around them with photons with higher energy coming to them, areas with slightly colder photons coming to them with slightly less energy. So they will be, at the time of recombination, a quadrupole around every electron, and the electron will therefore emit some polarized light that comes to you. And we have been able to, or we can decompose that light in 2 versions, an E mode and a B mode. So they have properties like the E mode, if you flip it in a mirror, it looks the same. The B mode, if you flip it in the mirror, it looks reversed. Like, it has handedness, as we say, because like your hands, it doesn't look the same in a mirror. And we know that B modes can only be made 2 ways. you can either take a normal E mode and have gravity deform it, twist it so that it becomes a B mode, or you can have gravitational waves make it. And the only B modes we should be able to see in the CMB are due to gravitational waves from just after the Big Bang, which are the source of those tiny fluctuations that will then become the seeds for stars, galaxies, the CMB, and its alternatives. We're still, unfortunately, looking for those primordial B modes. Simon's Observatory is one of 2 experiments currently looking at it. The other one is called BICEP and is at the South Pole. And maybe in a few years, someone will be able to give a talk saying, we have found the B modes. We now know the history of the universe down to the first instance, like 10 to the minus 20 or so seconds. So it's quite remarkable, right? This is just the theory part, but with the cosmic microwave background, we have been able to tell the story of the universe down to the first seconds. And if we found those B modes, we will go even further back in time to really fractions of a second after the Big Bang. But that's still for the future. So I mentioned gravitational lensing, and what I like about lensing is that it puts the CMB photons to work after they've been emitted all those years ago, and it can tell stuff about the universe from between when, like the universe after CMB was emitted. So light follows the paths shown to it by gravity. And so if, as the CMB photon makes its way through the universe, as the universe grows and expands, it goes through an area of high density because there is usually a star cluster or a galaxy cluster, a large area of dark matter, or just even a really massive object of any kind. It will curve around, and this is how like you can turn an E mode pattern in a B mode pattern by having the different parts of the light go through different lines of sight and have different curvatures. And so by measuring the map of the gravitational lensing of the CMB, we can say how much mass is between us and the CMB in any given direction. And coupled with models of light and galaxy formation, we can have like a sort of idea of how much matter there is in the universe and how much, and again, this can show us that most of the matter is going to be dark matter. Because we know, oh, there's this much mass between us and the cosmic microwave background. But all the stars, all the galaxies we see are like just 20% of the mass needed, so there must be some dark matter. Yes. Okay. Final part of the talk. It's all easy breezy. I'm going to talk about another effect. So after the cosmic microwave background forms, I said all the atoms have formed, right? And they're electrically neutral. So there's no light left in the universe except the cosmic microwave background. You're in some sort of beige fog. But as gravity collapses those atoms together, with nothing to stop them, enough start coalescing together that the pressure builds up and up and up and up until finally there is enough pressure for nuclear fusion to happen and a star to be born. So from this gas of hydrogen, the first stars are born. The stars, well, first of all, they have a lot of hydrogen to grow into, so so many of them can, so those stars are very massive. The first stars are like hundreds of times, thousands of times the mass of our sun. And they just start making light. And they make UV light, a lot of UV and X-ray light. And that light is energetic enough to start ionizing neutral light, neutral hydrogen around those first stars. So you have starting little bubble of ionized hydrogen forming around you. And so galaxies form, even more, the bubbles grow. black holes form inside those galaxies and start blasting the universe with UV light, ionizing it even faster, until in the end, most of the hydrogen is in galaxies, and most of the hydrogen is ionized, and normal light can just go through the universe. It doesn't. There's no it's not opaque anymore. It becomes transparent. So this is called reionization, and it is the process by which the universe goes from this neutral state, where there is no, there's more like absorption of light and then scattering, to an ionized state, where the universe is transparent to normal light. Yet there is still going to be some in the leftover intergalactic medium. There is going to be some ionized gas, and there are going to be especially a lot of electrons which have been kicked out by the ionization process. And those electrons, as in the primordial universe, will be able to get hit by CMB photons. And they will redirect. They will do two things. First, they will redirect the photons that come from different areas of the sky, which means that if you look at the path photon make, you will not see the photon straight from the. There's a probability you will not see the photon straight from the CMB, but one that has bounced on the electron since then. So, if you look at the cartoon on the left, the sphinx shell is the CMB. The photons travel through the neutral universe, hit an electron, maybe it goes like this. It hits that electron and then gets redirected in another direction, and it might take you to us. So that means that what you will see is not the primary CMB, but the CMB that has been smoothed by the redistribution of where the photons come from on the sky by this chance that they have interacted with the electrons. So if you look on the top left, I am changing the probability that the photon will hit an electron, which is that tau parameter, that optical depth to reionization, which is like how likely it is that you will hit an electron. And so that depends on several things, including how fast the first stars are going to turn you from a neutral universe to an ionized universe, how much matter there is in there, how much the first black holes have been blasting stuff around. And you can see that if tau increases or decreases, the amplitude of the CMB power spectrum that I showed in the beginning will go up and down, because you will have the CMB be smoothed or not smoothed by the chance it hits electrons. And it's sort of a source of confusion, because there's this other parameter, which is AS, the amplitude of those primordial fluctuations from inflation. The amplitude of the primordial fluctuations, and it acts the same. AS just scales the spectrum, scales the intensity of the hot and cold spots we see up and down. And so if you keep the product between AS and tau constant, the spectrum stops moving. You might have AS moving in one, like AS different from what you expect in one direction, tau different in the other direction, but because the product stays the same, you cannot tell which universe you're in. Fortunately, that does not apply in the E mode. Or that applies in the E mode, but not always. So what you need to realize is that each electron at the era of reionization will not see our CMB, it will see its version of the CMB. And because the universe is much younger, it doesn't see the 14 billion years we see now. It sees maybe 1 billion or 500 million years around itself. And so it will see a different realization, different version of the cosmic microwave background with the same statistical properties as ours, because it's the same universe. But while there's a tolerance for sure, it's the same quadruple. It might not be the same quadruple exactly. There is a bit of tolerance depending on like if you're in one part of the universe to the other. Even though like the processes that give rise to the cosmic microwave background are statistical, so the same physics might give you a different pattern on the sky within reason. You cannot go too far, but like there is a bit of tolerance. So you might see a different quadruple if you're sitting a billion light years away, but the power spectrum in its globality will stay the same. So those electrons, they will see slightly different quadruples, and so those will be correlated on the scale of what is called the horizon, which is the observable size of the universe at the time the electrons scatter the photon. And so that means that to us, on the sky, at the apparent angular diameter of the universe during reionization, there will be a correlation between what one photon sees and what one electron sees as its quadruple and what another electron sees as its quadruple. So, to make a very long story, and that is a very long story, a bit short, there is this, again, there is a likely correlation on scales of 30-ish degrees, 20 to, this is in logarithmic scale, which is why the ticks get closer to each other, but on scales larger than 20 degrees across the sky, which is, it's something like this. Yeah, something like this. On scales larger than 20 degrees, there will once again be a correlation, this time in the polarized light, because that's this angular scale of the universe for us at the time of reionization. And the height of that correlation is going to be proportional only to tau and not to the other parameter that scales up and down the main CMB spectrum, AS. So you need to, because it's a correlation on a big scale, you need a big area of the sky. So the best thing to do is to go to space. But going to space is expensive, so this next best thing to do is to build your $1 million telescope, hang it under a balloon made of nylon, and hope for the best. So, again, remember what I said, that you need to have less interference from the atmosphere. If you go up to the stratosphere 30 kilometers up, there's very little atmosphere left. You're almost in space, but not quite. So it makes sense. You can send a balloon with a telescope attached to it. So this is the launch of an experiment called SPIDER by some of my colleagues. They went to Antarctica, not quite the South Pole, but very nice. Assembled the balloon and launched it and had it fly for a couple weeks, pushed by the winds in the stratosphere around the South Pole, floating. And then at some point, the telescope ran out of a cooling fluid, and they cut the rope, have hopefully a parachute open, and drop the telescope down 100,000 feet, and hopefully recover most of it. It often works. Sometimes the parachute doesn't attach when you land, and so then the wind picks up, and you basically have a very efficient sled on the Antarctic ice. Some of our colleagues had to carry, drive 100 miles to recover all the trash that their telescope had left before it stopped just short of the crevice. So what I'm working on to measure tau is a balloon called Taurus, which will launch instead from New Zealand and fly for much longer than a couple of weeks. It's more like a couple of months. And basically, what our plan is in early 2029. So we're going to spend this year building the detectors, hopefully, and this big box, which is called the cryostat, which is where we put the cooling power. The next year, putting all the parts together, and then 2028, we're going to test that it actually works in different places, including currently spending a very warm and damp summer in a place in Texas, putting it all together, like doing a dress rehearsal of the assembly in New Zealand. And then early in 2029, we will go to South Island of New Zealand and attach it to a balloon. Hopefully it launches okay. And then it goes in the stratosphere, spins around, following the prevailing winds. And we either recover it in Australia or New Zealand or in South America, depending on like when the balloon decides that it doesn't want to float anymore. These things hopefully don't leak. NASA says, yeah, they're good for 100 days. None of them has made it past the 2 months mark. But they've gone up longer and longer and longer. So, you know, hopefully we get at least a month and maybe even more out of it. It's probably 2 months would be great. So yeah, Planck could afford to measure the sky for several years. We will only get a few months, but we have hundreds of times the detectors, which means we're hundreds of times as sensitive as Planck. And yeah, there is still the chance that even though we're above most of the atmosphere, there's a tiny bit of atmosphere. But apart from that, it should work. We're going to be the first people since Planck to observe at the frequencies in which dust is a major contaminant. We hopefully will make the best maps of the microwave sky at 1 millimeter, or 1/20th of an inch. I don't know. I think it was a metric system. But yeah, so that's what I'm excited about. I'm excited about attempting to measure one of the 6 parameters that make up the model of the universe better than ever before. And hopefully my colleagues find those B modes that tell us what the universe started like. And then we can stop doing CMB science because we will have figured out most things that we can figure out a bit. And we will move to more nice stuff about stars and galaxies. But yeah, what I want you to think about is that this one thing that was discovered by accident in the 60s can tell us the whole history of the universe and has kept giving us discoveries for the past 60 years and will give us discoveries hopefully for the next 20 or so years. Thanks.